Uh, Thank you. So can you see my slides? Yes?
Perfect, yes.
Fantastic. Thank you very much. Thank you for inviting me. It's really a pleasure to be here in the virtual setup. So I changed the title of my talk while preparing to this presentation, looking kind of in the landscape of other talks and making sure that, I'm not repeating the same things. And the big question that I kind of want to answer with the talk is, what kind of lessons did I learn after trying to develop algorithms for property prediction and other things during the pandemic? And I would tell you that my own perception and perception of members of the team at MIT quite changed after we realized the current landscape. And the work that I'm going to present is actually the work of a big group of faculty and students, and one of them would actually be the next speaker, Jim Collins. But I want to say that just before the pandemic started and, MIT closed, we had this paper with a big bunch again of students and faculty from Cell that demonstrates that you can, using machine learning techniques, identify a very potent drug. In this case, it was an antibacterial that works very well against multiple pathogens for which we don't have today. We didn't have a cure. And what was interesting that this particular molecule had a novel biological mechanism of action, and it was identified using primarily machine learning techniques, which were further validated in the biology lab. So we were very excited and saw that we really can contribute something, in search for antivirals during the pandemic. However, the reality check was that the situation that we had, when we developed the halicin, this antibiotic, is quite different when you're looking at the unraveling situation when a new pathogen appears. So first of all, there is very limited antiviral data, and the data that was released has significant noise. The screens don't agree with each other. So the assumptions that we typically make when we are thinking about, AI and drug discoveries, that we have, at least few thousand molecules, may not be even true. The second point was that we've discovered is that, we do a lot of work on de novo design, and in the situation when we are looking at the unraveling pandemic, it is unrealistic to assume that you can generate a new molecule, do all the testing, and actually bring it to the patients in some reasonable time, because the whole cycle of drug development and patient testing is very, very slow. The second point that we made, it relates to the virtual screening. So a lot of technologies that we are developing enable you to predict bioactivity of the molecules through virtual screening. So it turns out that, there are just maybe 20,000 safe molecules that everybody were screening, and you can as well screen them experimentally. However, it is still very important to develop these technologies because they open your door to other things. For instance, to compound combinations, which I will talk about towards the end of my talk. So at any rate, the technologies that I still believe is really important in the situation when a new pathogen appears is the technology of virtual screening. So what you want to do is to take a molecular structure and being able to predict some activity of interest. It can be some bioactivity, like being an antiviral. You also want to predict, the toxicity of this molecule and various physicochemical properties. And you want to do it in silico, assuming that you have very limited access to training data, and that you cannot do a lot of tests. So you really need to have a smart experimental design. So typically what you would assume in this case, that you're given molecular structures. Let's say we can think of them as 2D graphs, and they are associated with some measurement of activity of interest. And at this point of the talk, I assume that the algorithm really doesn't know what is this activity. This number can encode something related to being antiviral, or it can be encoding some toxicity related property. And then what we're going to do, we're going to take these molecular structures with associated activity and train our models to find patterns which map the structure into the activity reading. And the hope is that if you do it well, you can now take a new molecule and predict this bioactivity. So the key advancement that happened here when these models, came into play is how do you represent the 2D structure? And you can do it for 3D, but most of the models today are really working on 2D. How can you do it? So for a very long time, the idea of in silico screening was extensively explored in chemoinformatics, and the way they did it, they translated, the molecule into this fingerprint, which would typically encode some substructures that chemists identify as important to a given bioactivity. And then the goal of machine learning was just to learn how to weigh these different pieces together to predict activity. And of course, the accuracy of this technique was determined on how well do you identify this fingerprint. Did you pick up the right substructures and the right counts? So the major advancement here that came from neural network is that we actually automatically learning their representation, for instance, through graph convolution of the molecular structure, from which we can predict the desired score. And here you have much more flexibility, and you can encode the same molecule differently depending on the property you care about. So the hope is that if you do it well, what will happen, and here I'm showing, of course, 2D projection, that now you coded these molecules into these vectors where the distance between these molecular embeddings would be representative of the distance between the properties. So in this particular case, molecules that are close in the property would live together, like the two yellow kind of molecules, and then the ones which have very different property would live in a different part of the space. And again, the similarity here is not the structural similarity of the molecule. So again, we hope, and this is our kind of idealistic vision, that the distance in the molecular embedding space would be tightly related, maybe linear, when we are computing the distance in the property value. And, a while ago, what you've seen in the Holocene is actually the model that we developed at MIT. It's called Chemprop. It's a model which utilizes both Landler representation and fixed descriptors. We wrote a paper like last year where we tried it on millions, not millions, on 850 experiments. And, it worked reasonably well. It was consistently better than counterparts. I don't know if it is now consistently better because, people continue the development, and we kind of were very happy with the model. And we actually applied to the antivirals. We identified a number of new molecules and which were validated experimentally when we trained it on antiviral data. But I would say that I realize, through this half a year of pandemics, that we are very far from the point that we should be congratulating ourselves. And there are lots and lots of places where we should really improve the modeling. And I identify, that's pretty much what my talk is about, is identifying what are the areas, big areas, where we need to improve the technology. And I identify them here. So first of all is representation capacity, low resource training, mechanism understanding, and uncertainty estimation. So I would go through each one of them and kind of tell you how I think about them. So again, majority of the algorithms that translate from structure to properties are based on graph convolution. For those of you who are not familiar with it, the idea is very simple. You start with every atom having a representation by some vector, and here you can put your chemical knowledge and decide which features you want to use. Obviously, you can use degree and the type of atom and whatever. So you would have some vector. If you're really naive, you could say, I'm going to take all these vectors from different atoms and sum them together and say, this is my molecular representation. Clearly, it's going to be really bad because atom doesn't know about its own neighborhood. So one way to get the information from the neighbors is kind of to start exchanging messages where you take an atom and it takes a representation, these vectors from its neighbors. They are combined in some smart way. And then this atom, in this case, it's red atom, updates its representation. So, and the way we decide how you're combining, my own representation of my neighbors is actually driven by optimizing the accuracy of my prediction task. So after the first message exchange, I would know about my immediate neighborhood, but at the same time, me and all my neighbors are going to be updated. So when I do this operation again, I'm going to get information from more remote neighbors, and slowly, I will kind of get a view about what's going on in other parts of the molecular graph. Okay, so this story, sounds reasonable. Now I would show you the first place where it becomes maybe not as reasonable and intuitive as we wish to do. So at this point, every atom has, this kind of its vector, which it calls its own properties, some properties of the neighborhood in some way. And then what do? We just sum them up and call it, molecular representation. So it's really problematic because this kind of very simplistic aggregation of this set of vectors loses a lot of information. And here you can see on the bottom side of on the bottom part of the screen, you can see that you can have very different sets, very differently looking sets, which would have exactly the same sum. So it's too lossy of a compression. And we looked at different ways of how you can actually aggregate this information in a different way. And this is a work of my student Ben Sanjan and Octavian Ganea, when they said, how can we do this aggregation of these sets of vectors, which really preserve important structural information? And the idea was to use Wasserstein's prototypes. So you can imagine that now you take this big molecular space and you would have some sets of vectors, which we would call prototypes. We would actually lend them, but for the simplicity, assuming that those are kind of abstract molecules with their corresponding sets of vectors. And then when a new molecule comes in, it has its own length. So for instance, through the convolution vectors of sets of vectors, you represent the whole molecule, you aggregate them using the distances from this set of vectors to each one of the prototypes. And again, the whole model is learned jointly, and you are inducing both the prototypes themselves and the representation with a goal to optimize your prediction task. And what's interesting is to look how the representation learned using, graph convolution when you just sum them versus you're doing this more sophisticated modeling changes the latent representation. So here again, you see the 2D projection and the color represent the property. So what we would want to see, that we have this very smooth representation where we are, kind of moving from the dark blue to yellow, and we don't have, this kind of multicolored patches. And that's exactly what we see in the Wasserstein prototype representation. But when we look at the representation learned by graph convolution, we can really see that, the distance in the embedding space does not necessarily correspond to the distance in property values. And this is particularly acute because we know for many bioactivities we have property cliffs, and we can see that convolutional models don't handle them very well. There are many other ideas. I just gave you one, but you can see that there is a place here to improve. So the second thing that I want to talk about is generalization. And generalization is really, really an important topic because, I just took a picture from computer vision just because it kind of looks nicer, I think. But we all know that, when you dramatically reduce your training set, your model starts doing really funny things. And in the case, like in the current pandemic, as I said, the training sets are very small, very noisy. You need to be able to generalize well and to be able to do stuff, even if you don't have humongous data sets. Now, again, thinking about computer vision, you can say there was a lot of work on pre-training. So for instance, if you want to do, to process mammograms, you will pre-train your representation on ImageNet, initialize the model, and we know it would help. Similarly, you know, in NLP, even people who never took natural language processing class, you know, today know, you know, what is BERT, how you can create, you know, humongous amount of pre-training data through the auxiliary task based on word masking. And what was really remarkable here, I'm showing one of the data sets from natural language processing, is how much benefit using raw and annotated data through this pre-training mechanism help tasks where you have limited training data. So here you can see the graphs that I took from this paper below. You can see that this is one of the glue benchmarks, 11 NLP tasks. You can really see what a humongous boost these models got by utilizing raw data from pre-training. Unfortunately, and I know that Yuri's Leskovich is chairing the session. I know that the Stanford, you know, put an effort in trying to develop pre-training model for chemistry, and you know, it's very natural to think about it because you can say, oh, why wouldn't we do the same? We can mask, you know, presence of a particular atom. We can mask presence of particular substructure. We at MIT implemented these methods. We implemented the whole bunch of our own methods. We haven't seen anything close to what we see with pre-training in computer vision or in natural language processing. And I would say people who want to ask me a question and ask why is it so, I don't know. I mean, I have my guesses, but none of them are kind of empirically validated. I know we tried to empirically validate them. We didn't really got a clear signal, but this is really a hard task. We don't have today the pre-training methods which show significant improvement and enable you to generalize better. And I just briefly want to say again, another piece of our research, which was very much inspired by work on COVID, is generalization to new parts of chemical space. Because even if you have enough data and you're operating in one part of the space, many times you really want to generalize to a different part of the space where you have different classes of molecules, and you need to be able to do it. And that's why, again, for people who are not doing, you know, kind of chemistry AI, they may not be aware that the typical way to split training and testing data for this task is not random split as we do it in NLP or in computer vision, but actually do scaffold split, where your training looks very different from the testing because it's more representative of a realistic, you know, kind of drug discovery scenario. And when Gong, Jin, who is a student at Tommy and I are co-advising, develop a method which enables to perform this domain extrapolation via the algorithm that he called regret minimization. So what you want to do, you want to train the algorithm already in the condition when it would handle well domains it hadn't seen. And you kind of take your training data and you split it in some smart way to represent different types of domain. And let's say you have training set 1, where all the scaffold contain 2 rings, and training set 2, you have a scaffold that has cyclohexane. I cannot pronounce this word correctly, cyclohexane. And you train the model in such a way, you remove this domain 1, you remove examples from training set 2, you train the model on the molecules from this artificial set 1, learn the representation. You separately train the model on the domain 2, and you are formulating your regret as a difference between what the model does when it seen a representative from domain 2 and when it hasn't seen representative from domain 2. So it forces you to learn better representations that can generalize better. And I should say that there is a lot of work on invariant risk minimization and many other variants of you know, these ideas. I think there is really a lot of place here to adapt them to chemistry and improve model generalization. And what we have demonstrated in our experiment that it really does improve generalization capacity. I'm showing very briefly results on COVID when we see, you know, significant boost we got from this model. But again, I see it's really work in progress. Much more needs to be done here. I very briefly want, because, you know, the time is running, I briefly really want to talk about another area where I consider, you know, a big place for us to make an innovation. It's uncertainty estimation. You know, before I moved to this domain of AI chemistry, I didn't realize why uncertainty estimation is such a big deal, but it is a big deal because, you know, each time when you're making a prediction, somebody needs to synthesize this molecule, do the testing. So it's much more expensive than generating wrong machine translated text. So that's why people who work in pharma, in medicinal chemistry really care to get uncertainty estimation with a prediction. And there are quite a number of methods that are available today to do this uncertainty estimation. Many of them are pre-neural network methods. For instance, you know, you can compute the distance between your molecule in testing to the one in training. So those are distance-based techniques. So you can do it even in the embedding space, or you can do ensemble model when you know, cut your training into different subgroups, train the ensemble, and give high certainty if different models agree, so on and so forth. I put you the examples of these models. So here again, very bad news. We just published a paper about it that demonstrates that we didn't find among these very commonly used methods, when we applied them with you know, neural models like Chemprop, we didn't really see any consistent answers. So the way we assessed whether this uncertainty method actually do something useful is if you use them to decide, you know, top 1% or top 5% and compared the accuracy with a general prediction, we really didn't see any values. In some cases, actually decrease the accuracy of the model. So again, the area where we need to think algorithmically how to solve it. And the final area that I want to talk about relates to mechanism understanding. So again, one of the lessons that, you know, I discovered when we were working on Halicin with John Stokes and Jim Collins is that after we did our prediction, which was an easy part, then they went into the lab for another many months to try to identify what was the mechanism of action. And the hypothesis that we have, you know, it's really important, you know, why the molecule does what it does. And there are two pieces that we're interested in. One is to say, can you, whenever you're doing prediction, can you tell me why did you make this prediction? But the second point is that, again, especially in the case of new pathogen, when the time is a matter, maybe if you really incorporate biological knowledge into the prediction model, you can get, you don't need so much screening data. Maybe the model can generalize better. So this kind of brought us to the idea that you need to bring biological modeling directly into the models that learn structure. In this particular case, this is my son who is homeschooled. Now, so in this particular case, what we want to do is to take our molecule and to predict the targets, and then from targets to predict the bioactivity. And what we discovered when the information, you know, when kind of there were the first publication about COVID, we see that there were a lot of information available about targets. And there are some publications here that you can see that were widely available even before the screening data was available. So the question is, can we incorporate it? And that's exactly what we've done. We built this model again that takes the compound, models drug-target interaction, predicts this drug-target interaction fingerprint, and from there we predict the disease activity. What was very interesting here is that when we kind of use the targets that people published, and there were several you know, publications from Nature that specify those biological targets, that when we did it the first time, it really didn't work. And the, opening, what made the big difference is actually expanding this drug target interaction profile with latent targets, which is just, imagine that you have more latent variables that the model can predict, which are used afterwards to predicting the antiviral activity. So the assumption here is that whatever is published about targets is only very limited knowledge, and there is, a lot of other things that's going on, and we want to provide our models with opportunity to figure it out. And when Marinka Zidnik recently gave a talk on this topic, we've seen that she came from very different approaches exactly, to the same finding that, that the published targets cannot explain the full picture. And actually we have a mechanisms that enable us to discover, at least to some extent, what are these hidden targets. And what I want to say is that one of the kind of direct application of this approach was an ability to look at drug combinations. And again, for the case of COVID, we had data released by NCATS, and we're very, very grateful to them for this release. And you can see that they did really, limited screening. It was, I think, 160 or so pairs of molecules. So you cannot train, normal models that expect thousands of combination, what we have in the cancer data sets. We really want the model to learn when you have very small combination data like here, that you have information about the targets and you have information about single compounds. We come up with this specific model architecture that can actually, again, separates this modeling the combination activity to different sub-pieces when you are looking for each drug, what kind of targets it's involved. Then you're looking at the combination of the targets that they do jointly. You assess a synergetic activity, and then you predict the combination effect. And here, the access to targets was crucial. And you can see the results of the prediction of this model. We show the results on the left and right, and the blue one shows that you don't provide any target information. You consider all the targets as latent variables. The orange color shows the case when you do provide known information about the targets, and we see that there is some boost in performance. We also look at two sets of targets. There were several papers published about the targets, and we also demonstrated that the model can discover additional targets. In this case, we kind of, during training, didn't provide to the model information about targets from reframe, and demonstrated how you can uncover this information through the model training. Those are examples of some synergistic combination that we recently discovered. The reason is, recently, we just last week got results from NCATS, which did the empirical testing of our prediction, and several of the combinations that we found were actually showed strong synergistic effect. But I would like to again say that I just see everything that we are doing work in progress, and I cannot say that we really find definitive solution for any of these questions like representation, generalization, low resource training, mechanism understanding, uncertainty estimation. I think each one of these areas are crucially important for developing, models that can on demand identify new therapeutics. And I think that here we really need, as a computer scientist, identify, new algorithms which don't exist today, which would be targeted for these tasks. So with that, thank you.
Thank you very much, Regina, for a very, very nice talk. We have a number of interesting questions, and there was a little debate on our QA board about why would you use neural networks to encode molecules, and how do you make sure that your representation is valid?
So the traditional way to encode molecules was, as I said, fingerprints like Morgan fingerprints and other fingerprints, where you would just say, you know, if it has this ring or this substructure, I know it may correlate with my activity. I will record it as a feature vector and then learn to predict. And, you know, in some cases, this chemoinformatics model were there for at least a decade or two. And again, for certain type of assays, they were doing well. Now, the problem is that if you're moving to new bioactivity properties, many times you don't really know what are the substructures that really are important here. And as a human, even as an expert in the field, you have limited capacity to do so. So what neural networks enables you to do is kind of to take this graph and map it into a vector, which is optimized for your prediction task. What we are losing here is interpretability of this representation, because it previously knew that the first coordinate would correspond to this ring. When you did this translation, you actually don't know what it means. And the only way for us to know whether it is valid is to see if it helps us in our prediction task. So as I showed at the beginning of my talk, this kind of idealistic picture, let me just go faster. At the beginning of my talk, I showed, you know, what we want to have, which is, you know, this mapping, which puts molecules, which may be even different structurally, very close in this space. And how do we know if we achieve this goal? We can see how well our model predicts the activity of interest in new test set that we haven't seen before. So this is a way. And I don't know if there are people from medicinal chemistry. I should say that in this paper that I referenced from Chemprop, we identified that there were several classes of assays where actually these manually created fingerprints were better than the land model. Those were assays where we had limited training data, when the training data was noisy. So at the end, the best model that Chemprop has that work reliably across many data sets, it actually combines land representation and a fixed fingerprint. So I think that they have different strengths and weaknesses as to representations, and it's worth to explore, yeah, you know, which one is more appropriate for the data you have.
Super. Thank you so much. One sub question is, how much data do you need to be able to train these representations? You know, how many molecules do you need?
Yeah, so this is a great question. So we've seen in our paper, this is the case when we've seen in the paper, that, you know, for a few thousand molecules, it can already predict, assuming that you have, you know, that your data is clean. Because, for instance, for the halicine, our original training set was maybe 2,000 molecules, which is very small. Now you can ask, is it true that if now I give you 50,000 molecules, you're going to be much better? So, and then the question is, how accurate is an assay, how reproducible it is? For instance, we see that the assays which are empirically challenging, which have a high noise, are also, of course, challenging for the algorithm to learn because there is a noise in training data. But I think that, you know, given what we observe right now, you know, a few thousand, it's already a good starting point.
Super. Thank you. Another question is whether you have optimization of molecular properties.
So, sorry, excuse me, I was so excited to see you.
Yes. Super. So, multi-objective optimization of molecular properties. Do you have any thoughts on that? For example, improving toxicity and binding affinity.
Yeah. So in this presentation that I gave, I just focus on one technology, which is you know, this virtual screening. When given molecule, you want to predict something. So to identify molecule which have property A and property B, you can just, you know, run both of them on zinc and identify intersection of the two sets. Now, many times when people think about multi-primed optimization, for instance, you already start with something, you already have your favorite hit and you want to optimize it. So in this case, we have the whole suite of generative model, which do de novo design. And for those of you interested, our most recent paper really looks on how to make this optimization being able to work on many, many properties. And it's very close to how medicinal chemists are thinking about this problem. So this model kind of lends to identify pieces that drive property A and pieces that drive property B and so on. And then it learns how to put them together to generate coherent molecule, really kind of mimicking what medicinal chemists do. But for those of you who are interested in kind of multi-parameter optimization, I would really encourage to look into the, generative models. And we have the whole suite of them and other people as well.
Super. Thank you very much.